In this lecture, we are going to look at the ADC module on the PIC 16F877 microcontroller. The PIC 16F877 is one 10-bit ADC that can convert analog inputs from 8 possible channels into a digital output. The channels are named AN0, AN1, AN2 through to AN7. The channel currently being converted to ADC is selected in software. The positive reference voltage for the ADC is supplied either from the positive supply pin of the PIC VDD or the positive reference voltage pin VREF+. The negative reference voltage is supplied either from the negative supply pin of the PIC VSS or the negative reference voltage pin VREF-. The clock that is used by the ADC is either derived from the clock of the PIC or from an internal RC oscillator. The diagram shows the structure of the ADC. We can see the 8 input channels AN0 through to AN7. Then we see a block that is made up of switches. The switches can be used to select the channel that supplies the input to the ADC. We also see 2 other switches that are used to select the positive reference voltage and the negative reference voltage. The switches are all operated in software by setting certain bits to certain states. That's the pin out to show the pins that are used with the ADC. The ADC pin functionalities are multiplexed with a number of other pin functions on the PIC. Let's look at the registers that are associated with the ADC. First are the registers ADRESL and ADRESH. These are the registers that are used to hold the result of the analog to digital conversion. The lower byte is stored in ADRESL and the higher byte is stored in ADRESH. The two registers avail 16 bits for the result. However, we only need to use 10 bits. Therefore, the result can be either left justified or right justified. When right justified, the higher bits are set to zeros and the lower 10 bits are available as the ADC result. When left justified, the lower 6 bits are set to zeros and the upper 10 bits are used as the ADC result. Left justification can be used to make the ADC to be used as an 8-bit ADC. In this case, only the result in the register ADRESH is used, and that makes the ADC to work as an 8-bit ADC. Articon 1 is a register that contains bits that are used to control the operation of the ADC module. ADCS1 and ADCS0 are bits that are used to select the clock frequency for the ADC module. There is a third bit that is used in the selection of the clock frequency, and that bit is located in the register Articon 1. CHS2, CHS1, and CHS0 are the bits that are used to select the AD channel that is currently being converted. Go done is the bit that is used to start the conversion process. AD on is the bit that is used to turn on or turn off the ADC module. These are the bit combinations for the bits CHS2 through to CHS0 that are used to select the channel that is currently being converted. ADCON 1 contains more bits to control the operation of the ADC. ADFM is the bit that is used to select the format of the result. That is, it selects between right justified format and left justified format. ADCS2 is the bit that is used together with the bits ADCS1 and ADCS0 in ADCON 0 to select the clock frequency for the ADC. PCFG3 through to PCFG0 are the bits that are used to assign the functions of the pins between ADC input channels, digital I/O pins, and reference pins. The table shows the bit patterns for the bits ADCS2 through to ADCS0 to select between the different available clock frequencies. The table shows the bit patterns that are used to configure the functions of the pins. As an example, if the bits PCFG3 through to PCFG0 are set to the bit pattern 0010, the channels AN0 through to AN5 are set as digital I/O pins, and the channels AN4 to AN0 are set as analog input pins. The positive reference voltage is VDD and the negative reference voltage is VSS. Trace A and trace E are important registers to also consider when working with the ADC module. These registers contain bits that are used to configure the port directions of the pins. Analog input pins and reference input pins must be configured as inputs in order for them to work effectively in the ADC module. If you are going to work with the ADC interrupt, you would need to also consider the registers INTCON, PIE1 and PIR1. INTCON contains the global interrupt and peripheral enable bits. PIE1 contains the interrupt enable bit for the ADC module, and PIR1 contains the interrupt flag for the ADC module. These are the steps that may be followed when running the ADC module. Number 1, assign and configure pins for use as analog and reference pins as desired using the registers ADCON 1, trace A, and trace E. Number 2, select the analog input channel, the ADC conversion clock, and turn on the ADC module using the register ADCON 0. Number 3, if desired, enable the ADC interrupt. 4, wait for the acquisition time. This time is nominally 20 microseconds. 5, start the conversion process by setting the go done bit in the register ADCON 0. 6, wait for the analog to digital conversion to complete by polling the go done bit or waiting for the AD interrupt to OK. Number 7, read the ADC result from the registers ADRESH and ADRESL. Number 8, clear the bit ADIF, which is the ADC interrupt flag, if required. We have a tutorial exercise here. In this exercise, you are required to develop a C program that can be used to configure and use the ADC module on the PIC 16F877. You can optionally upload your response through the Google Classroom platform. And here is a laboratory exercise. In this exercise, you will be required to design a digital scale based on the ADC module on the PIC 16F877. The comprehensive lab sheet shall be uploaded on the Google Classroom platform. Please attempt this laboratory exercise and upload your responses through the Google Classroom platform and as according to the instructions in the laboratory sheet.